We are live. Okay, quantum mechanics and the periodic table. So, this is the last of chapter 2. Sorry for the delay, things happen. Alright, so, valency. Remember I discussed valence electrons and core electrons previously. So, the outermost shell, okay, or level. Okay, just quick reminder. We have N, L, M sub L, M sub S. Okay, they describe properties of the electron, and they are also more or less the location of the electron. So, level or shell is N. That is the broad location. Then we have sublevel or subshell is L. That is a subdivision of N. So every level is made of at least one sublevel. Okay. Then we have orbitals, so that every sublevel is made up of at least one orbital, and then just spin. So the electron either has spin up or spin down. And the outermost level of the atom is where you find the valence electrons. We also encountered the term valence back in chapter 1 when we were talking about the discovery of the periodic table. So where valence was how many atoms can atom X bond with. Okay. So valence originally meant how many atoms can atom X bond with. Now we use valence to refer instead to the outermost level of electrons, because those are the electrons that can form chemical bonds. So the terms are in that way related. So let's close the camera. The outermost shell is the valence electrons. Everything else is core electrons. That is the broad description, and it kind of works. So here we have carbon. Its innermost electrons, the first energy level, is the core electrons, and then the second energy level is the valence electrons. Nice and simple. Those two core electrons, those represent the or those have the same electron configuration as helium, just 2 electrons. Okay, so here we have carbon, total of 6 electrons. Here we have helium with 2 electrons. So 1s1, 1s2 is helium, and then carbon is 1s2, 2s2, 2p2. I'm going over this again because electron configurations and energy levels and sublevels and so on are very important. So, popping back over, 2s2, 2p2, the outermost energy level are valence. Okay? That is very simple, very straightforward. It works very, very well. The situation gets more complicated when we look at larger atoms. So, for iron, the previous noble gas absolutely, definitely are core electrons. Okay? For iron, that is... Here we go. Iron is element 26. The previous noble gas is argon. So the first 18 electrons absolutely are core electrons. Oops. Then, according to the simple definition, the 4s electrons definitely are valence. Okay? The 3d electrons, there it gets more complicated. Okay? They're technically not the outermost electrons, but they do get involved in chemistry. For iodine, once again, we're looking at a larger element, the previous noble gas. Let's pop back over to our periodic table. The previous noble gas from iodine is krypton. So those are definitely core, those first 36 electrons. Okay. Then the 5th energy level, the s and the p electrons there, those are definitely, absolutely valence electrons. The 4d electrons are definitely core. Okay. So the reason it's more complicated with iron is because of degeneracy. Okay, let's bring back up. Boom. So for iron, looking at that situation, We have 4s, hello Wesley Pup, and 3d. Okay, so there's 2 s electrons in 1, 2, 3, 4, 5, 6 electrons in that d subshell. Oh, that is not focused at all. Come on, there we go. Okay.
There's a free piano down by the dumpster.
Awesome. All right. So these are definitely valence. Most of these guys are core, okay, because of degeneracy. This guy is unpaired, so he's valence. Okay? But because of degeneracy, because of the fact that these guys all look exactly the same, they have that same spin, and they're in the same subshell, they are honorary core. Okay? They don't want to go anywhere because there's 5 of them in that same sublevel. They have a lot of degeneracy. They're very, very stable just where they are, so they're not going to go anywhere. That's why the situation is more complicated with iron, and it explains some of the behaviors of iron. Okay. Now, the reason I'm going over valence and core again is because valence electrons are very important when it comes to understanding chemical properties and chemical behaviors. Okay. So, for example, when it forms an ion, when it interacts with non-metals to react, okay, it'll form ionic compounds. It does so by losing electrons. And the 2 ions it forms are iron 2+ and iron 3+. It will either lose 2 of its valence electrons or 3 of its valence electrons. And we can see that that's where they are. That's what they are. At first it loses those 2 s electrons. Hello, Sasha. And then it will lose that d electron. Come on over here. Yep, follow the pen. Okay. And so then the 3rd electron it loses will be that. And that is where iron will stop when it comes to forming ions. It doesn't want to lose any more electrons because these guys are stable, they're happy, they're not going anywhere. All right, so let's close the camera. Let's pick the cat up off the desk, put him in my lap, where he will not want to stay because he's not yet learned to be a snuggle bunny. All right, so a better set of rules for valency and core when it comes to understanding chemical properties, chemical behaviors. The previous noble gas, okay, when you're talking about the electrons of an atom, the electron configuration of the previous noble gas is definitely, absolutely core. So, again, looking at iron, the previous noble gas, argon, the first 18 electrons, definitely core. 1s2, 2s2, 2p6, 3s2, 3p6. Okay, those guys, absolutely core. Okay, so that's what we're looking at. Boop, 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 here. Okay, that is the electron configuration of argon, previous noble gas, definitely, absolutely core. Degenerate d electrons or f electrons count as core. They're honorary core. You don't abbreviate them. Remember, you don't abbreviate them as the previous noble gas because they're not part of the previous noble gas, but they still count as pretty much core because of degeneracy. So, and when I say degenerate, I mean when you're looking at a half full or completely full D or F sublevel. Okay, so these d electrons, 5 of them are honorary core. Only 1 of them will act as a valence electron. That's why I mean kind of valence there. Okay, so a half full subshell is going to be valence. A completely full subshell is going to be valence. Or sorry, core. A half full subshell will be core. A completely full subshell will be core. Okay. S and p electrons will all in the outermost level. S and p electrons, the outermost level, are definitely valent. And I want to go ahead and edit this slide. Outermost level, S, P, and so on are valent. Okay, so let's boop, 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 boop. Okay, so when you have S and P electrons in the outermost level, they're always going to be valent, and non-degenerate D and F. So if you're not looking at anything that's part of a Any electron in D or F that are not part of a half full or completely full level are going to be valence electrons as well. The more degenerate they are, the more reluctant they are to participate in chemical reactions. All right, so when you're looking at the periodic table, every group on the periodic table, remember a group is a column. So every atom in the halogen group has the same valence. Okay, so we look at fluorine, 1s2, 2s2, 2p5. Okay, it ends at 2p5. Chlorine, 1s2, 2s2, 2p6, 3s2, 3p5. It ends at 3p5. So 5p electrons, 5p electrons. Bromine, likewise, ends at 4p5. Iodine, 5p5. Astatine, 6p5. So they all end with 5p electrons. They all have the same valence situation going on there. So that is why they have the same kinds of chemical properties. And that's why the periodic table, remember, was grouped this way, was because they had the same sorts of chemical properties. So that is why the periodic table has this weird blocky shape, is because the S sublevel starts at the first energy level, then the P sublevel starts at the second and third. The D sublevel technically starts at third, but it doesn't really show up until after 4S because, again, of the splitting of the sublevels. Okay, so that's where these things come from. And this was arranged by chemical properties. The chemical properties are because of electrons, and the electrons have those level sublevel arrangements. So that is one of the ways we can talk about the periodic table. We're going to be spending this particular video talking about various properties of atoms, of elements, and how they are due to things like valence. Okay. So first we're going to talk about shielding and effective nuclear charge. So sodium, just a quick reminder, the 11th element, so it's right here. Okay. Sodium has 11 protons. Around that we have a core of 10 electrons. Okay. The previous noble gas from sodium is neon, 10 electrons. It has a single valence electron there in the third level. And then so 10 core electrons, 1 valence electron. Okay. So electrons have negative charge, protons have positive charge. So the electrons are attracted to the nucleus. They are pulled in by the nucleus. Okay. So that is why the electrons are held to the atom. So that valence electron there on the outside is pulled toward the nucleus. But in between that electron and the nucleus, you have the core. So the core is acting as a shield because the core has a negative charge. So in between the positive nucleus, let's bring back the pointer. In between the positive nucleus here and this negative valence electron out there, you have this big old buffer of negative core electrons. So they're acting as an electric shield, more or less, blocking the influence of the nucleus. The nucleus is pulling on that valence electron, but not much of that positive charge makes it through that shield. Some of it obviously does. Otherwise, that electron wouldn't be there. Okay. So effective nuclear charge is, okay, remember Z, capital Z, we used that to represent the atomic number, how many protons there are in the nucleus. We have ZF, effective. Okay, so effective nuclear charge is how much of the nucleus the valence electrons can feel. How much of the nuclear pull makes it through the core electron's shield. Okay. So it's just the number of protons minus the number of core electrons, which means it's equal to the number of valence electrons. Okay, so sodium has 11 protons, it has 10 core electrons, and it has 1 valence electron. 11 minus 10 equals 1. That is going to work very straightforwardly for all of the main group elements. Okay? So 1 valence electron in this column, a valence of 1. 2 valence electrons in this column, a valence of 2. When you start talking about the d electrons, the d block, it gets a little bit more complicated, and we sort of ignore those. So we just sort of pop on over to the p block. Valence of 3, valence of 4, valence of 5, valence of 6, valence of 7. Okay. So effective nuclear charge increases from left to right along the periodic table. Because the core is remaining the same size as you move from left to right. Here on the third row, for example, we're looking at, let's bring up a periodic table with names on it. Here on the third row, we're looking at sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, right? They have the exact same core. The previous noble gas for all of those elements is neon. So the core for all of them is going to be those same 10 electrons. But we keep on adding electrons in the valence shell. Okay, we keep on adding protons to the nucleus as well. Sodium has 11 protons, magnesium has 12, aluminum has 13. So more electrons, more valence electrons and more protons, but the core is remaining the same size. So core of 10 electrons, 11 protons, reach through the 10 electrons, we have 1 left over. 12 protons minus the 10, we have 2 left over. 13 minus 10, we have 3 left over. 14 minus 10, we have 4 left over. The reason it gets more complicated for these guys is, again, because of that degeneracy, because of the way the half-full and completely full subshell works. And also because we get those weird anomalies where the chromium group promotes an s electron to get the half-full shell, and the copper group promotes the electron to get the completely full shell, right? So that's why we sort of leave those by the wayside. It's a little bit too complicated. We don't have the easy little mnemonic for remembering just 1, 2, 3, 4, 5, 6, 7. Okay. So valence increases from left to right. Effective nuclear charge increases from left to right. It stays the same when you're within a group because they all have the same sort of valence. They all have the same setup, the same situation. The core increases when you go down. Okay, it goes from 2 to 10. Okay, when you're going from the second row to the third row, it goes from 10 to 18. But you've also increased the number of electrons, okay, by the same amount. So the valence remains the same. The effective nuclear charge remains the same. The first column, the effective nuclear charge is 1 all the way down. The second column, the effective nuclear charge is 2 all the way down. All right. So now we can explain the atomic radius in terms of effective nuclear charge and energy level. Atomic radius means the size of the atom. How large is the atom? Okay. So energy level makes a lot of sense. Every time you go down a row on the periodic table, you're going out in energy level. Okay, so the first energy level is really close to the nucleus. The second energy level is further from the nucleus. The third energy level is even further from the nucleus. The fourth energy level is further from the nucleus. Okay, so every time you take a step down in the periodic table, bloop, you're going out in energy level. The atom just bloop, gets that much bigger. So you can see here a sort of representation of the sizes of the atoms, going from hydrogen to lithium, boom, from lithium to sodium, boom, sodium to potassium, boom, you just get bigger. The numbers underneath these atoms, those are the actual atomic radii, in, I believe, picometers. Pico is the thing below nano. So instead of 1/1 billionth, it's 1/1 trillionth, 10 to the negative 12. So don't worry too much about that. Just know that lithium is about 3 times bigger than hydrogen. Sodium is not that much bigger because the third energy level isn't that much bigger than the second. The fourth energy level isn't that much bigger than the third, right? So they're getting bigger, but it's, anyway. The point is that the bottom of the periodic table is going to be bigger than the top of the periodic table when you're moving within a group. Okay? As you go down the periodic table, the atoms get bigger. Now, the situation is different when you're moving within a period, when you're going from one group to another. Because within that row, The core, the energy level remains the same. What's changing instead is the effective nuclear charge. Okay? You're increasing the number of protons, you're increasing the valence, but the core remains the same size. Okay? So that means that the nucleus is able to pull harder and harder on the valence electrons as you move to the right along the periodic table. Okay? So going from lithium to beryllium, the effective nuclear charge increases from 1 to 2, and the atom gets smaller. Okay? So lithium is 167 picometers, beryllium is only 112 picometers. And then you take another step over to boron, the effective nuclear charge goes up to 3, and boron goes down to 87 picometers. Carbon, 67, nitrogen, 56, oxygen, 48, fluorine, 42. Okay. So as you go from left to right along the periodic table, the atoms are getting smaller because of effective nuclear charge. As you go down along the periodic table, the atoms are getting bigger because every step down you're going out in energy level. So that means that the biggest atoms are down here in the lower left. Okay. They have the highest energy level and the lowest effective nuclear charge. The valence electrons are really far away from the nucleus, and there's a lot of shielding in between them and the nucleus. So those atoms are just really, really big. Meanwhile, the smallest atoms are here in the upper right because they're at the lowest energy levels. So the electrons are just playing closer to the nucleus to start with. And then they have the highest effective nuclear charge. There's more nucleus able to get through the shielding. So the nucleus is able to pull really hard on those electrons. So you get the smallest atoms here in the upper right. Okay. So those are the trends. The atom size increases as you go down and left on the periodic table. Atomic radius decreases as you go up and right. Okay. So they could ask you, they'll never actually ask you to give a number for the size of the atom. There's no way you can actually predict the actual size. But what you can do is you can compare atoms. You can compare the sizes of two different atoms. So they can ask you to compare two atoms within a row. Okay, within the same period, they could ask you to compare those two atoms. Like between manganese and iron, which one is larger? Well, the one further to the left is the one that's going to be larger because it has a lower effective nuclear charge. When they're in the same row, they're in the same energy level, so the difference is the effective nuclear charge. They could also ask you to compare within a group. Okay? Same column, different rows. In that case, they have the same effective nuclear charge, but they have different energy levels. So the one lower down is going to be bigger because it's an energy level further out. The one higher up is going to be smaller because it is an energy level further down. To make things more complicated, they could also go along the diagonals. So here we have a comparison between gallium and cadmium. Gallium is further up and to the right, cadmium is further down and to the left. It's a double whammy. You take a step down, the atoms get bigger. You take a step left, the atom gets bigger. So gallium is going to be smaller, cadmium is going to be bigger. Okay, the numbers are a little bit covered, but gallium is 136, cadmium is 155. What they won't do is ask you to go down and right, because there the trends are acting in opposite directions. You go down one, the atom gets bigger, but you go right, the atom gets smaller. Now, if you're just doing one down and one right, this one is going to be bigger, just because an energy level is a much bigger change than just a difference of one effective nuclear charge. But it is kind of unfair to ask you to go down and right because the trends are asking in opposite directions. The other three are fair game. Within a row, definitely. Within a column, definitely. Along the this diagonal, northeast, southwest, that is perfectly fair. This one is mean. They won't do it unless they make a mistake. I have seen them do that. One time they asked you to compare carbon and chlorine, which down one and then right four, which is... It's difficult. That's very, very difficult. Very difficult. And I would not have known that chlorine was bigger without having this chart available to me. Okay, so they will not ask you to do that. Okay, within a row, within a column, or on this diagonal. Okay, the helium to cesium diagonal. Okay, top right to lower left. That is the main diagonal for the periodic table. This diagonal, top left to lower right, it don't mean crap. Okay. Yes, Sasha, that's right. Play with the camera. That is exactly what it's there for. You are my sweet little Sasha. All right. So that is atomic radius. No, please stop playing with the markers. I need those, and I don't want the dog to eat them. All right. So, come on. Why are you not advancing? What the heck? Did we lose the rest of the... Oh dear. That is... Okay. I'm going to go ahead and open up... Oops. Okay. Okay. I didn't think that was the end of the slide. I thought there was more. So what I'm going to do is I'm going to wing it. I'm going to go into Blackboard, going to open up the textbook, and I'm going to check to make sure, because there's probably more. What the heck? That might in fact be it, but I'm going to... Ow, 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 stop biting my hand. Course content. Okay, so getting started. Let me check the learning objectives. Come on. There we go. Oh. I mean, I should trust that I knew what I was doing when I made these slides, but that then kind of surprised me by how quickly it stopped, and I want to double check. Come on, open up. Okay, we're looking at chapter 3. I don't want to look at chapter 3. I want chapter 2. Specifically, oh, it looks like it is supposed to end with atomic radii. Okay, good. I didn't screw up. I am slightly competent. Okay. Just because I'm paying attention to you doesn't mean you get to eat the pens. Okay, it does end with atomic radius. Okay. All right, good. I was worried there for a minute. Okay, so that is what they're going to ask you in terms of the properties based on the periodic table. There will be more. That's why I was somewhat confused. There are more properties that we will cover later, but not for this test. All right. So now I'm going to go ahead and go over these last 5 questions that I wrote up here in this worksheet. Okay. About orbital filling diagrams, electron configurations, effective nuclear charges, and comparing atoms. Okay. So, first up, we have question 1. Draw the orbital filling diagrams for carbon, calcium, and copper. All right. So, we open up this guy. We see how much the cat is kind of in the way, but I can move the camera. Okay. So, carbon has carbon has 6 electrons. You do not want to sniff the marker, baby. All right. So 1s, 1, 2, 2s, 3, 4, 2p, 5, and 6. All right. So remember, an orbital filling diagram is when you actually draw out the individual electrons. All right. Next up was calcium. Calcium is element 20, but I want to double check that to be sure. Yes, it's poop. element 20 right here. So that means we're looking at 20 electrons. So this is going to take a little bit longer. One S, 1, 2. 2S, 3, 4. 2P, 5, 6, 7, 8, 9, 10. 3S, 11, 12. 3P, 13, 14, 15, 16, 17, 18. 4S, 19, 20. All right. So that is the orbital filling diagram of calcium. Just a quick reminder. Those are the valence electrons. Just those, the 4s electrons. All right. And finally, copper. The orbital filling diagram of copper. So copper is right there, element 29. All right. Sasha got bored. So element 29, we're looking at 29 electrons for calcium. Sorry, copper. So copper, 29 electrons. And once again, just to save myself a little bit of time, the last electron for copper will be in the 3D subshell. Okay, remember 1, 2, 3, 4. It's on the 4th level, but the D sublevel is shifted, or the D block is shifted by 1. Also, just to save a little bit of time, I remember that copper, the 9th column, that is one of the exceptions. So we bump 1 electron out of 4s into 3D. Okay. So 1s, 2s, 2p, 3s, 3p, 4s, 3D. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and we leave that one unpaired because it's going to go in here. 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. All right, so those are the orbital filling diagrams for copper, calcium, carbon, calcium, and copper. Okay, all right, so let us move on to the next question. Write out the electron configurations for fluorine, titanium, and lead. All right. Remember the electron configurations, instead of drawing every individual electron, we are just listing the levels and sublevels. Okay. So fluorine is first. Fluorine has 9 electrons. So 1s2, 2s2, 2p5, 2 and 4 and 9. All right, so that is the electron configuration for fluorine. Okay. I knew that I had to stop at 2p5 because, once again, we come over here. Fluorine is in the second row, 1, 2, it's in the P block, and then 1, 2, 3, 4, 5, the 5th column. So we're stopping at 2p5. Now titanium, titanium, it is right here, 22 electrons. It's got 4s and then 3d. Okay, so that is where we're going to stop. 4s2, 3d2. So, once again, all right. So, titanium with 22 electrons, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d2. Okay, so 2, 4, 10, 12, 18, 20, 22. And finally, we have lead with 82 electrons. If I were to try and count them out as I went along, that would be a major pain in the butt, which is why I do not do that. That's why I have this, we're going to end in the p block. We're going to end on the 6th row. There's 2 p electrons. So we're going to stop when we get to 6p2. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f14. Don't forget that the F block is shifted by 2, the D block is shifted by 1, the F block is shifted by 2, and F doesn't show up until after 6s. All right. So 5d10, 6p2. So that is the electron configuration for lead. 2, 4, 10, 12, 18, 20, 30, 36, 38, 48, 54, 56, 70, 80, 82. All right, so those are the electron configurations, and remember, we don't really care about most of these electrons. So core, let's see, core, okay, so those are all definitely absolutely core. Titanium doesn't really have any honorary core. The only candidate would be the 3d electrons, but there aren't enough of them. So these guys don't have the degeneracy necessary to act as honorary core. It only kicks in when you have a half full or completely full D or F subshell. So that means that these two are honorary core. Okay. Completely full D and F. So degenerate, 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 degenerate. Okay. Thus, they are honorary core. Meanwhile, we have valence electrons. Ow. I'm not trying to play, Sasha. Over here. Over here. Okay. So valence, valence, valence. Okay, and when Sasha gets out of the way, you will see that I have underlined the valence electrons for fluorine, titanium, and lead. All right. Ow, that's my hand. Okay, so fluorine, titanium, and that's the mouse. Don't play down to the stereotype. You're better than that, Sasha. Ow! Don't attack the mouse. Or the mouse pad, for that matter. Okay. So there's that. Now, abbreviated electron configurations for fluorine. Let's see. I gotta see if I can show you this. All right. Okay, so next up, abbreviated electron configurations for iodine, gold, and francium. You notice I went for the bigger atoms for the abbreviated electron configurations because they aren't nearly as annoying. So, iodine, gold, and francium. First up, we have iodine is right here, element 53. To abbreviate, we need the previous noble gas. The previous noble gas is krypton, element 36. Remember, previous, not closest. The closest would be xenon, but that's next. So you can go all the way to the right and then boop, up 1 to get krypton. So for iodine, we have krypton, and then it is in the 5th row. Yes, the 5th row. So it's going to be 5s2, 4d10, 5p5. Okay, it's in the, come on, focus. Okay, it's in the 5th row of the periodic table. 1, 2, 3, 4, 5. It's in the p block, and it's in the 5th column of the p block. So 1, 2, 3, 4, 5. So 5p5. That's where I end. I think for future videos, I'm definitely going to have to kick Sasha out of the recording studio. Okay. So next up, we have gold. So gold is AU. Okay, remember, AU is gold, AG is silver. When somebody gives you gold, you say, "Aw, you really love me." And if somebody gives you silver, you say, "Ah, you don't love me." Okay, so that's how you remember. AU is gold. Okay. So back over to the periodic table. Gold. Now you're chewing on my water bottle. Or a goofy cat. All right, gold is right here, element 79. Previous noble gas is xenon. So, really quick, previous noble gas is xenon. So that takes care of the first 54 electrons. And then, coming back over here, gold is on the 6th row, so this is the 5D. And then it's in the 9th column, along with copper. Now, because it's in that 9th column, it has the odd sort of behavior. It's going to promote from the S group into the D block. Okay? So it's not going to start with 6s2, it's going to start with 6s1. So xenon, 6s1. Then remember, the 6s is followed by 4f14, and then 5d10. It would be 5d9, but we promoted out of S into D. Let's see if opening the blinds a bit. There. Now he can watch people playing in the swimming pool. Oh, and it's a little brighter in here. That's nice. All right. And then finally, we have francium. Okay, oops, that's francium. There we go. So francium is way down here, row 7. It's in the 1st column. The previous noble gas is radon. It's element 86. So this one's going to be really easy. 1st column means it only has 1 valence electron. So for francium, abbreviate radon 7s1. That is so much easier because that radon, oops, not RR, that's supposed to be in. All right, because radon takes care of the first 86 electrons, and then we only have the one we care about, the 7s electron. All right. Thought cats were supposed to sleep all day, Sasha. God. Okay, so now we go back to the worksheet. All right. Okay, cat's in the way. What is the effective nuclear charge on carbon, chlorine, barium, and bromine? So carbon, chlorine, barium, and bromine. So that's boom. Notice I did not ask about any of these guys. Okay, we have carbon, and then chlorine, and then barium, and then bromine. Okay, so these are all main group elements. That's what you're going to get in the periodic. That's the sort of question you're going to get. We're not going to ask effective nuclear charge for any of these guys. Now, we will probably ask you to, we might ask you to compare the sizes here because that follows the same sort of trend. But we're not going to ask you to give the effective nuclear charge because that's complicated. Main group elements, really straightforward. So carbon is in the 1, 2, 3, 4th column here of the main group, so it has an effective nuclear charge of 4. Chlorine is in the 4, 5, 6, 7. It's in the 7th column, so it has an effective nuclear charge of 7. Then barium is in the 2nd column. It's right here, so that means it has an effective nuclear charge of 2. And then bromine, well, it's right underneath chlorine, so it's going to have the same effective nuclear charge. It also has an effective nuclear charge of 7. Now, finally, which of each pair is larger? First up, we have boron versus carbon. Boron versus carbon. Well, boron is here, carbon is here. They're in the same row. So we're talking about effective nuclear charge. The trend for the row is effective nuclear charge increases from left to right. So carbon has a higher effective nuclear charge. Its protons can pull harder on those valence electrons. So carbon is going to be smaller and boron is the larger atom. Further left is larger. Larger on the left. Larger on the left. Larger on the left. All right. Next up, carbon versus silicon. Carbon versus silicon. Okay. Silicon is right below carbon. So every step you take down is a step to a higher energy level. I know that's going to be confusing, but you step down is a step out. So bloop, silicon is bigger than carbon. 3rd energy level versus 2nd energy level. The electron's just that much further away from the nucleus. Okay, so silicon is bigger than carbon. And finally, carbon versus chlorine. This was on a test at one point, and so I decided to adopt it because you just can't compare these. Because you take a step down, it gets bigger. You take several steps to the right, it's going to get smaller. So these, it's really, really hard to judge. You cannot make the determination upper left and lower right. Okay, that is the diagonal you cannot operate on. You could compare fluorine and sulfur very, very easily. Fluorine is way up in the right. Sulfur, you take a step down and you take a step left. Sulfur is just going to be bigger. But carbon versus chlorine, you can't make that comparison. Not easily. Not unless you have a handy chart of actual atomic sizes available right here. 67, 79. Okay, chlorine is still bigger. All right, so that is it for the questions I had thought up. That is it for Chapter 2. So this week is going to be about finishing up Chapter 2. Sometime later this week, I will do videos in which I walk through the end of chapter problems. So I recommend that you study by working on those, and then if you're having trouble with any of those, you can come and check out the videos and see how I work through them. How I solve those problems won't necessarily be the only way. It might not even be the best way to solve the problem or think about it, but it's how I solve the problem and it's how I think about it. So at the very least, it will be an effective way of doing that. It's one way of doing that. All right, and that is it for this particular video. I will see you around.